So now that we have discussed about breakdown mechanisms in gases, let us see what are the breakdown mechanism and how it actually breakdown proceeds in solid liquid materials. We will afterwards, after we've discussed solids, we'll also go on to discuss liquids and composite materials. But right now, let us concentrate on solid materials. Now, solids after gases, the most commonly used kind of matter which is used for insulation are solids. And as I have mentioned to you earlier, when we choose a dielectric material for insulation in a particular application, the first thing that we are looking for is, of course, its dielectric properties. However, we are also interested in its non-electrical properties. We're often interested, for example, a liquid you might use, as I told you before, you might choose to use a liquid insulator, where liquid material as insulation, when you're not only interested in providing insulation, but also providing cooling properties, for example, in transformer oil. Solids are used where you need to provide mechanical support. So you take the conductor, you put a solid insulation, the solid insulation provides insulation, but it also might be supporting the conductor and providing mechanical support. So solid materials provide mechanical support for conducting parts and at the same time insulate the conductors from one another. But you might imagine that if you have an irregular volume and you need to fill that up with a dielectric material, a solid may not be a very good choice. And in that situation, what we might be doing is we use the solid because we need to provide structural strength, we need to provide mechanical support. But in addition, we may incorporate a gas, and that gas will fill up the spaces, the blanks that are left between the conductor and the insulator. So frequently, especially when we are using solids, we would be using a combination of solids with a liquid or a combination of solids with a gas, and this is something that we will discuss. It comes with its advantages and with its disadvantages, and this is something that we will discuss when we talk about composite materials, composite insulator materials. Right now, let us concentrate on solids. Now, before I start talking about breakdown mechanisms, look at this plot. This plot has, on the x-axis time, on the y-axis it has breakdown strength. I have not provided any units because this is just a qualitative curve. But if you look at this, don't look at the mechanisms right now. If you look at this graph, what you see is the breakdown strength of a particular material can deteriorate considerably over time. So for example, at the outset, you apply a field across the material. At the outset, the breakdown strength may be very high, whereas the material, as time progresses, the same material may have considerably lower breakdown strengths. And let us imagine that I have applied a particular value. I've applied a particular value of the breakdown. I've applied a particular field across a particular material. Let's say this is the field. Now, initially what you see is, this particular field, I mean, it's a little curved, this line is, imagine that it's exactly a straight line. So this particular voltage or strength, we are not really concerned with voltages, this particular stress that you have applied is much lower than its breakdown strength, so you don't have a problem. But if you keep the voltage on for long times, and when you have come to, let's say, some region, okay, this is not quite correct choice. Let me choose another value. Give me a minute. Let's say this is instead the value of the voltage. Let's say this is the value of the voltage that I apply. So initially, as you see, the breakdown strength is much lower than the breakdown strength required. The stress is much lower than the strength, and you don't have a problem. But you keep the voltage applied for long periods of time, and when you have crossed something like 10 to the power 1, so 1 second, after that, that same value may lead to breakdown. So the point is that a particular value of the stress, applied stress, which may not be problematic at small values, at small times, may be problematic at longer times, because the reason that that particular stress does not cause breakdown at short times but causes breakdown at longer times is because of the particular mechanism involved. So depending upon the time frame, various kinds of breakdown mechanisms can come into operation, and depending upon the breakdown mechanism, breakdown may or may not happen. What I mean by this is, let us say, if for example, if you see that a particular material breaks down at times lower than a couple of seconds, you might well imagine that the processes which are operational, which lead to its breakdown, are these processes. These are intrinsic, avalanche, and electromechanical processes of solid breakdown. I will explain them a little later. Between a few seconds and up to around 10 to the power 4 seconds, normally the breakdown mechanism which is responsible for the dielectric breakdown is a thermal mechanism. And if you're looking at failure of solid materials beyond this time, so when the failure develops over a long period of time, greater than 10 to the power 4 seconds, actually not just greater than 10 to the power 4 seconds, this might be something that happens over a very large number of years. In that case, the processes that must be responsible are erosion or electrochemical processes. So basically what I'm saying is that there are certain processes, breakdown in solids are possible by various mechanisms. There are certain processes which take a very long time to progress. But once you give them the time, they can cause breakdown at very particularly low stresses. Whereas other processes take very little time to develop, but they need much higher breakdown stress. They need much higher stresses. They can withstand much higher stresses, and the breakdown strength is higher. So let us take a quick look at what these stresses are. What kind of breakdown mechanisms are operational at these various times. As I say, the shortest breakdown mechanism, which takes the shortest time to develop, is the intrinsic breakdown. And you can imagine from the name that intrinsic is something that is an intrinsic property of the material. So here we are talking about the material in its pure and homogeneous form. So it is just a this intrinsic breakdown strength is a characteristic of the material. It's a material property. The material is pure. There are not too many impurities. The material is homogeneous. The temperature and environmental conditions are controlled. There are no external discharges. There are no random factors. So perfectly controlled situation, if you can imagine. And in that situation, breakdown happens. It is likely to take place due to the intrinsic nature of the material. Intrinsic nature of the material, or it is due to the intrinsic dielectric breakdown strength of the material. However, most often, this is a very theoretical concept. You will not have a situation where you can control everything in this manner. You can control impurities, you can control ambient conditions, you can control any random factors. So what will happen is, when you see a breakdown in practice in the laboratory, even under reasonably controlled conditions, it is very likely that it will be due to some other mechanisms which we will discuss later. Intrinsic breakdown is very difficult to achieve in practice, but if you do, this intrinsic breakdown strength of most materials are very high, and the intrinsic strength is a property of the material. It is also a property of the temperature, but it is not a property of many other factors which we will see actually govern breakdown of a material. So this is the first mechanism that we have discussed, the intrinsic breakdown mechanism. Experimentally, the intrinsic strength is very rarely reached. What is the process by which intrinsic breakdown happens? Okay, the intrinsic breakdown is accomplished in times of the order of 10 to the power minus 8 seconds. So this is almost an instantaneous breakdown. You apply the stress and almost instantaneously breakdown happens, and the stresses that you need are well in excess of 10 to the power 6 volts per centimeter. Intrinsic breakdown is caused by a mechanism which is electronic in nature. So the electrons are responsible, free electrons are responsible for breakdown. Now in a dielectric, you would of course have not too many free electrons, and essentially electrons are present in the valence band, and by whatever processes, only when these electrons acquire enough energy to cross the Fermi level, to cross the forbidden energy gap, and it can come out from the valence band to the conduction band, then you have free electrons which can take part in the conduction current. So essentially, you need a very large quantity of energy to ensure that enough conducting electrons are produced in the material, and they can cause intrinsic breakdown. But that is not always what happens, especially if you have even a small amount of impurity, and sometimes even if you don't have impurities, you will find that there are certain electrons which occupy what are called shallow traps. What are these shallow traps? Now, this is something that is important to us because we will be discussing trapped charges later. So the conduction band is at a particular energy level, and there might be electrons present in the material which have energy content which is just a little lower. So their electronic energy level of these electrons are just a little lower than the conduction band. So these are called shallow traps. So there will be electrons present in these various shallow traps. The shallow traps are energy levels which are close to the energy level of the conduction band. So what happens is, even if you cannot provide a very large quantity of energy, which is needed for taking electrons from the valence band to the conduction band, if you provide an energy del W, which is enough to extract electrons from these shallow traps and bring them out in the conduction band, so then you can make do with a smaller quantity of energy. So what I'm saying is, it is possible that there are trapped. So when electrons are present at these shallow traps, they are called trapped electrons. And by the release, so if you provide sufficient energy such that electrons from the trapped levels can come out onto the conduction band, you can have enough electronic charge carriers which can ultimately lead to breakdown. Or even if you do not have shallow carriers, you might have trap levels which are much closer to the valence band. So very far from the shallow traps. So in that case, you need much larger energies for an electron which is in the deep trap to release its electron onto the conduction band. But you still need less energy than you need to get an electron from the valence band to come out into the conduction band. So in intrinsic breakdown, you have a situation when the electrons, which may not be in the valence band, but maybe in these intermediate shallow traps or deep traps, and they gain sufficient energy from the applied field to either entirely cross the forbidden energy gap from the valence to the conduction band, or they may be detrapped either from shallow traps or detraps. So of course, remember, we are not talking about very impure materials here, but only very, very, very small impurities, and maybe there are sufficient quantity of energy from the valence band in addition to detrapped electrons from the shallow traps and deep traps, which combined, and you have sufficient number of charge carriers now in the conduction band. After that, these electrons must gain energy from the electric fields and must produce an avalanche, just as we have discussed in case of gases. So they have to cause ionizing collisions. There has to be enough electrons, secondary electrons, which are released by these electrons, and only then intrinsic breakdown can happen. As I said, this is more theoretical in nature. It characterizes the material, but most of the time in practice, you will be in trouble because breakdown will happen due to some other kind of mechanism. So this is about intrinsic breakdown. At low temperature, the trap levels will be mostly filled with electrons. At room temperature, some of the trapped electrons will be excited thermally into the conduction band, because, as I said, shallow traps and conduction band have very small energy gaps. And then you apply a field When you apply a field, these electrons which have come out, they will have inelastic collisions between themselves. This energy will be shared by all the electrons. As a result, the electron temperature will rise, and this will also help in more trapped electrons to come out from the conduction band. As a result, the material's conduction will increase and a complete breakdown will eventually reach. So intrinsic breakdown, you have electrons from the valence band and from the various trap levels coming out of the conduction band, and they must cause further collisions to create an avalanche. There will be a temperature rise, and avalanche will happen, and only when all these things happen will you have a situation where intrinsic breakdown is possible.